AB Calculus, section 7.3, page 4. We are going to be finding the volume of a solid that's created when the region enclosed by y equals the square root of x equals 4, and y equals 0 is revolved about the line y equals 3. Let's start off by sketching a graph. We have y equals the square root of x here. X equals 4. And y equals 0, the x-axis. This region here, we're going to take this and spin this about the line y equals 3. This point right up here, where y equals square root of x hits x equals 4, that's occurring at the point 4, 2. Y equals 3 is then this line right here. And we're going to take this shape and we're going to spin it around up this way. The distance between this point 4, 2 and that line is 1 unit, so I know that 1 unit on the other side is where that piece is going to hit. This distance is 3, so it's going to be way up here. I'm going to end up drawing right over my words, but that's all right. We have this piece up here, and this is spinning around the line y equals 3. To put some ovals in here and show that three-dimensional nature of this. And this is spinning out this way. Putting a representative slice through here. It's going to slice right through this way. And we are going to have a washer. Here's the hole in the middle. And then here's for the solid part out there. This is hard for you to imagine. I'm going to turn it this way, and we have a cylinder of ice cream here, or peanut butter, and we've started scooping out that ice cream, and as we scoop deeper into this cylinder, it gets more narrow. Sides are kind of coming in here, if you will. Alright, then to find this volume, we know we have a washer. So we are going to add up a bunch of pi times big R squared minus little r squared times thickness. And the big radius goes from the axis of revolution up here at y equals 3 all the way out to this outer edge out here. And if you look, no matter where we slice, if it's out here in the middle or out here at the end, that big radius is always the distance from this horizontal line y equals 3 down here to the x-axis, and that is always a distance of 3. So that big radius, 3 squared, minus then the little radius, and the little radius is from this line y equals 3 on down to that square root of x curve, to that curve. There's your little radius right here. That is a y value, but it's not strictly y. Y is this distance here. From the x-axis up to that curve, that's y. So that little radius is 3 minus y. And we'll have to square that. all times thickness, and our thickness here, we're slicing through this way, this way. These are dx slices. Problem with our variables, we have x's here and y's inside of there, so we'll need to change out this y with the square root of x. That quantity is squared. All of this dx. Bounds would be from start slicing to stop slicing, or 0 to 4. If we clean this up a bit, 9 minus, when we square out this piece, that's going to be 9 minus 6 square root x plus x dx. Oh, and look at that, 9 minus 9 gone. And then we are going to have plus 6 square root x, and then minus an x. And you can go ahead and evaluate that through on your own and make sure you can come up with 24 pi is that final answer there. 24 pi, final answer. Let me erase this out. It looks like a minus sign there. Make sure you can handle that integration by hand. All right, now comment. Discs and washers use elements of area that are perpendicular to the axis of revolution. Looking at this case here, this solid, spinning this about the x-axis, and we have discs here because this is solid in here. These are dx slices. This one's spinning about the y-axis. We would slice through this way. These are dy slices. Okay, so let's come down here, and I want you to find the volume of the solid that's created when this region bounded by y equals 3x minus x cubed, and y equals 2, and the y-axis is revolved about the y-axis. So go ahead and grab this thing on your calculator, or graph that, not grab it, but graph that on your calculator. Oh, I need to add a few words in here. When the region in the first quadrant, I forgot that. When we graph this cubic looks something like that. We want the part in the first quadrant, so that much. Y equals 2. Y equals 2 hits there, right there. That maximum value right there is at 1, 2. And the y-axis, so this region right here, we're going to spin that about the y-axis. Wish I had done this in pencil first, because then I could have erased out all of this. But I don't want any of this stuff. I only want the part in the first quadrant. So I'm going to go back and erase out all that part. This over here is, even though it's in the first quadrant, it's extra. We don't need it. Because we are just revolving that tiny region right there. When we spin that around the y-axis, we get this piece over here, and we have a funnel going on. Solid all the way through. So this is going to be a disc. When we set this up to find volume with a disc, we're going to add up a bunch of pi r squareds times thickness. Alright, radius goes from the axis of revolution to the original function, which is out this way. It's running horizontally. right here. That is an x value, so that will be x squared, times thickness. We're slicing through this way, so our slices are dy slices, and our bounds will be from where we start slicing down here at 0 up to where we stop slicing, which is at 2. Getting our variables to match, we need to replace out these x values here with y values, which means we'll need to come over here to this function and solve that function for x so that we can replace out this x and get y's. And you can try and do that. That's not possible. When you've got different powers on that x and that second variable y, you cannot solve for that variable that's a degree 1 and a degree 3. It's just not possible. So we run into trouble over here trying to find that volume because we can't solve for x. We're in trouble. We can't solve for x. Don't quit. We're going to have to try something else. And that something else shows up on the next page. Please join me.